awfully quiet today. He normally asks hundreds of questions. Not today.
Not today.
Not today, huh? It's a Monday. All right, so now what we're going to do is the following. So, oops, this is the one I want. Okay, so I'll give you the punchline. So here is a circuit, and there's the battery, there's the inductor, and there's the resistor. Okay, so what I'm going, so you see this switch is a 3-way switch. When I move the switch from here to there, when you move the switch from here to there, what you're doing is you're removing the battery. Okay. So as long as the battery is there, you have a current flowing like this. This is a steady state current, and in the steady state, there's no induced EMF. So this is sort of the simulation. That's wrong there. Anyway, so now what we'll do is we'll remove the battery. So there is a battery. We remove the battery. Look, there's still a current flowing in. Okay, and by the way, this end should be positive and that end should be negative. So in the simulation, that's a mislabeling. But anyway, we'll ignore that. Okay, so here's the steady state current again. I'm going to remove the battery. And look, there's still a current flowing in the circuit. So any idea about what's going on? Okay, so here's what's going on. Okay. When a steady current is flowing through a solenoid, what is happening is you learn over several slides that energy is stored in the solenoid in the form of magnetic fields. Okay, and when you remove the battery, the energy stored in the solenoid is driving this current. Okay, and it's able to drive it for a few milliseconds. Okay, and then the current goes to zero. Once the stored energy in this goes away, the current goes to zero. So that's what's happening. Okay. And now what we want to do is we want to get the functional form for this current. And you can see that it's an exponentially decaying current, but we want to get the functional form for this current. Okay. So I as a function of t is what we want once we remove the battery. Okay. So again, like we said, we're all mathematical experts. So let's model that system. So here's the system. We're going to flip the switch from there to there at time t equal to 0. And then we want the current in this circuit. Okay. I'll come to this differential equation in a second again. All right, so here's another look at that thing, sort of a different one. So when you open switch 1, you're removing the battery. And so this one is better, you just flip the switch from there to there. When you flip the switch from there to there, you remove the battery and completed the circuit. The same thing is accomplished with 2 switches here. You open this and close that switch. Okay. And so when that switch is closed, the battery is driving the current. And when that is open and this is closed, the energy stored in the inductor is driving the current. Okay. Anyway, I like this one better. So we'll flip from here to there. And we want to find the current in this circuit. Okay. So let's go to the whiteboard. Okay. So okay, so we saw that at t equal to 0, when we remove the battery, the current started flowing in this direction like that. And we wanted to find I as a function of t. That's what we want to find. Okay. Again, we are going to lean on Mr. Kirchhoff to come up with a mathematical model for this circuit. So what we'll do is we'll use sum of voltages across a closed loop is 0. We will start at this point. Okay, we're going with the current, so it's minus IR. Okay. And then we come across here. Okay, the current is decreasing. Okay, it's so since the current is decreasing, this end will become positive and this end will be negative because it wants to drive the current. It wants to keep the current increasing. Anyway, so the current is decreasing. The voltage across this is minus L di by dt. Equal to 0. You see di by dt, this is negative. So negative of negative will be positive, and that makes sense because this end would be positive, negative. So when you go across this element, you'll get a positive voltage change, and this is positive because di by dt is negative, and negative of that will give you a positive term. So now the differential equation is ITR plus L di by dt equal to 0. So there's the differential equation modeling the behavior of this system. Okay. So here's your mathematical model for this system. And again, you can solve this equation. Okay. So, and you can find this is equal to I naught, current at time t equal to 0, E minus t by tau. That solves this differential equation, and tau is the time constant again. So the current decays exponentially. Okay. So here is the current, and E was the original battery that was connected. So E by R was I naught, and the current is decaying exponentially. Okay. So again, what we did was we modeled this system. We saw that the current in this thing was decaying exponentially, and here is the functional form for the current. And again, tau, the time constant is L by R. Okay. So again, let's go to that simulation. All right. So, okay. So what we're going to do is we're going to remove this battery and just have the energy stored in the inductor driving this current. And we found the functional form for this current. The current was exponentially decaying. Okay. And that was the idea. And again, let me emphasize, see, for typical values, these changes are happening over milliseconds. Okay. All right, so now we have looked at an RL circuit. An RL circuit is a circuit which has a resistor and an inductor. And these are connected in series. Of course, you can connect them in parallel, but we're not studying that. Okay, so we're studying the simplest case. Again, let me make sure we understand that. Okay, so what we have studied is a resistor and an inductor in series. Okay, of course, you can connect them in parallel, but that'll cost you a little extra to study, so we're not going to do that. All right. So now we're going to, let's go back to the simulation. Again, while the battery was there, we all understand that the battery can drive a current through the circuit. When we removed the battery, there was still a current for a few milliseconds. And we asked the question, so what was driving this current? And I gave you the answer. I said that there was energy stored in magnetic fields in this inductor, and that was driving the current. Okay. So now we are going to get an expression for that energy stored in the inductor. Okay. So energy in the magnetic field. An inductor resists an EMF from establishing an instantaneous maximum current in the RL circuit. So what this bullet is saying is when you close the switch, the battery is trying to establish current in the circuit, but this inductor is fighting it. So as the current is increasing, induced EMF is opposing that change. So the battery is having to do work to establish that current, okay, to its maximum value. And when you do work, you're storing energy. So for instance, when you lift a box up, you're doing work on the box, and so you're storing gravitational potential energy in the box. Okay, so just like that, when the battery does work, it must be storing energy, and it turns out it's storing energy in the inductor. So the battery does work to establish a steady current, and in the process stores energy in the inductor. Okay. So we'll get an expression for that. Okay. Again, we'll use Kirchhoff's rule to come up with the differential equation for the behavior of this system. So we'll close the switch. Now let's go to the whiteboard. All right, so yeah. So we're going to use Kirchhoff's rule. We'll start off in this corner and go counterclockwise. Okay. Kirchhoff's rule is sum of voltage across elements should be 0. Okay, so we'll go across this element, and by the way, so let's call this IT, current as a function of time. We'll go across this element, so that's plus E minus ITR and minus L di by dt equal to 0. So that equation says E equal to I R plus L di by dt. Okay. Now we'll multiply both sides of the equation by I. Yeah. And so this E by I, E times I, this is the rate at which the battery is delivering power to the circuit. This is the rate at which this guy is dissipating the energy. This guy is dissipating energy. So the rate at which money is being pumped in, this guy is spending the money at that rate. And this, so this must equal the rate at which this guy is saving the money or storing energy. So the rate at which energy is being delivered, this term is the rate at which energy is being dissipated, and the rest of it is being stored. And so that's what that term is. EI equal to I square R. And what we're going to do is write that term as L times d by dt. Oops. L is constant, so what we'll do is d by dt of 1/2 Li squared. Okay. Yep. When you take the derivative of that, we 2I times di by dt, the 2 will cancel that half, and so you'll get this term. So I've just rewritten that term like so. Okay, so now, again, this is the rate at which the battery is delivering power. This is the rate at which the resistor is dissipating energy. And so energy delivered is rate at which it's spent plus the rate at which it's being stored. again, d by dt. So this is the energy that is the energy stored in an inductor at any instant. All right, so there's the differential equation that models that the behavior of that system. After you close the switch and you rearrange that term, EI is the rate at which power is delivered. EI is equal to I square R plus DI by d by dt of 1/2 Li squared. Okay. Hence, the rate at which energy is stored in the inductor is given by that, and so 1/2 Li squared is the energy stored in the inductor at an instant when the current is I. So when the current is 0, the energy stored in the inductor is 0. Okay. And when the current is maximum and its steady state value, that's when the maximum energy is stored. Okay. So that's the energy stored in the inductor, and you had proof of that. You have proof of that in this simulation, where you saw that that stored energy could drive this current, even after you remove the battery. Okay. So that was proof of that. All right, so now what we're going to show you is that the energy stored is stored in the form of magnetic fields. In a previous chapter, you saw that capacitors store energy in the form of electric fields, and inductors store energy in the form of magnetic fields. Okay. All right, so the energy stored is 1/2 Li squared. The inductance of that solenoid is given by that, mu naught times N squared. N is the number of turns per unit length, and AL is the volume of the, A is the cross section of the inductor, and L is the length of the inductor. So this is the volume of the inductor. The magnetic field inside the solenoid is mu naught, the magnetic field inside this solenoid. So in an ideal solenoid, that blue lines are the magnetic fields, they're uniform and strong, and outside the fields are 0. But the inside field is given by mu naught Ni. So in this expression, we're going to substitute that 1/2. We'll put this expression for L, and for I, we'll solve for I from here. It's B naught, I is B divided by mu naught N, and we'll substitute that. Okay. Anyway, after you substitute all of that, here's what you get. B squared by 2 mu naught times the volume of the solenoid. So what this tells you is this is the energy per unit volume in the magnetic field. So for 1 meter cube of this field, that much energy is stored. Okay. So if the field were 0, the energy stored is 0. Okay. So the energy density, or energy per unit, energy divided by volume, so energy per unit volume. Energy per unit volume is equal to B squared by 2 mu naught. All right, so what we are saying is energy is stored. So in the capacitors chapter, you saw that energy is stored when electric fields are generated. Oops. So energy is stored when electric fields are generated. Okay. So in a capacitor, when you charge a capacitor, you've stored energy in the form of electric fields. Okay. Now what you're seeing is in a magnetic field, when a current passes through a solenoid, you create a magnetic field, and energy is stored in magnetic fields as well. Okay. So anytime you generate an electric or magnetic field, you're storing energy. Okay. So very important concept to remember. And the energy per unit volume is B by 2 mu naught. And you guys realize that as soon as the current in the solenoid goes to 0, B will go to 0, and the energy stored will go to 0. Okay. Now, the most important application of these solenoids are these mutual inductance is transformers. Okay, so you've seen transformers. You see little transformers stuck on electric poles near your homes. And what these transformers do is step up and step down voltages. So, and these works with transformers work only with AC circuits. Okay, so here is an AC source connected to N1 number of turns. And this is soft iron, a magnetic material that couples the magnetic field strongly to a nearby loop. So you see, this loop doesn't have a battery. Okay, so this AC source is changing the current in this loop, which is in turn changing the magnetic field in this loop. And the soft iron couples that magnetic field strongly, and that induces an EMF. So the voltage induced in circuit 2, it turns out is equal to the number of turns here divided by the number of turns in the primary coil times the primary voltage. So for instance, let's say this is 10 volts, the amplitude is 10 volts, let's say, and N2 by N1 is 100. That is, this guy has 100 times more turns than this. So 10 times 100, you get 1,000 volts out of it. Okay, so you applied a voltage of 10 volts, and what you got was 1,000 volts out here. Okay. Similarly, if N2 was less than N1, the voltage would be smaller. Okay. Now, so a transformer can be a step up or a step down transformer. So V2 equal to N2 over N1 times V1. If N2 is greater than N1, V2 is greater than V1. This is a step up transformer. And if N2 is less than N1, V2 is less than V1, and that's a step down transformer. Okay. Now, for a step up transformer, you got a higher voltage. So one would think that we got free energy, but it turns out that V1, I1, the input power is equal to output power if there is no dissipation. Okay, so there is never free lunch ever. So in a step-up transformer, if the voltage increases, the output current is lower. Okay. All right, anyway, transformers are very useful devices because losses are minimized when power is transmitted to the highest possible voltages. So let's say electricity is generated at Hoover Dam, and then it needs to come thousands of miles across to your home. And so to transmit the power from Hoover Dam to your home, you have to transmit at high voltages, and you use step-up transformers near Hoover Dam, and near your house you use step-down transformers. So voltage step-up and step-down transformers are used for power transmission. Yeah. All right, I am going to pause now because this is the last important topic we'll talk about, LC circuits. Okay.